So let's move on to the simplest model, the tier 1. This is what is called the saturation vapor pressure model. So the scenario here is, if you can consider a sealed container that is half filled with liquid of a pure chemical and half filled with pure air in the head space above the liquid. And the liquid phase chemical molecules with sufficient kinetic energy escape the liquid and enter the head space air. And as the molecules collect in the head space, some of them strike the surface of the liquid and condense back into the liquid phase. When the rate of evaporation equals the rate of condensation, the system is at equilibrium and the headspace air is saturated with the chemical vapor. And at that point, the partial pressure exerted by the gas phase chemical molecules in the headspace at equilibrium is alternatively termed the chemicals vapor pressure, equilibrium vapor pressure, or the saturation vapor pressure, P sub V. According to the ideal gas law, the mole fraction of a constituent, denoted by Y sub I for the ith constituent, is equal to its partial pressure divided by the total pressure, as shown in this equation here. And the airborne concentration of that ith constituent in parts per million, or ppm, is equal to its mole fraction multiplied by 1 million, or 10 to the power 6th. And you have encountered this particular equation in the previous lecture when we talked about the rules of thumb. The worst case assumption is that the chemical's partial pressure in air will equal its vapor pressure value. This is equal to saying that the chemical's airborne concentration is the same as its saturation concentration in air. So what you can sort of picture in your mind is that there is this worker standing in a pool of this liquid in a completely sealed room and is breathing the air that is now saturated with this particular solvent's vapor molecules. This worst case assumption requires that the chemical is continually exposed to the room air. So the pool of this liquid at the bottom is exposed to the room air. There's no room ventilation, so Q is 0 cubic meters per minute. The room and liquid temperature are constant. There is sufficient time to reach equilibrium so that the liquid phase and the gas phase molecules are in equilibrium, and the rate of evaporation of molecules from the liquid surface is equal to the rate of condensation of the molecules back into the liquid phase. And there is sufficient mass of the chemical in the room such that the liquid remains at equilibrium, meaning that the liquid doesn't completely evaporate and you're left with a dry floor, for example. And then finally, the ideal gas law holds. So what would be a scenario where this might be applicable? So let's say that there is a perchloroethylene container that is left open in a non-ventilated chemical storage cabinet that is completely sealed. And an employee opens the door, and the first whiff of breath that he or she takes when they open the door and they get exposed to the cabinet air, they are exposed to saturated vapor pressure concentration of perchloroethylene. So to what ppm concentration of perchloroethylene is the employee exposed in the first couple of breaths? So let's assume that we know the temperature, it's 20 degrees Celsius. We know the partial vapor pressure for perchloroethylene, it is 14 millimeters of mercury at 20 degrees Celsius. And we'll assume that the pressure in the cabinet is 760 millimeters of mercury. That is the standard atmospheric pressure at sea level. So we will assume that the employee was exposed to saturated concentration of perchloroethylene at 20 degrees Celsius. And we are assuming that the equilibrium vapor pressure was attained in the cabinet and the contaminated air was not significantly diluted by room air prior to inhalation. And so that's why I said in the first couple of breaths, what is the concentration? So we can use the equation that I talked about earlier. The saturated concentration in parts per million is the vapor pressure of perchloroethylene, which is 14, divided by the total pressure, which is 760 times 10 to the power 6. And so the answer is 18,420 parts per million. So this is the highest concentration that can be observed in nature for perchloroethylene at 20 degrees Celsius. Perchloroethylene cannot physically attain a higher concentration than this at 20 degrees Celsius. So I just briefly want to go back to my previous lecture on the rule of 10 and remind everybody that if there is some amount of air movement, then we can use the rules of thumb, the rule of 10 especially, to estimate what the fraction of saturation is for a particular scenario. So we can use this very simple model, the saturation vapor pressure model, in conjunction with our rules of thumb, as shown in this slide. Let's look at another example where we can use this idea of saturation vapor pressure concentration. So let's look at the air displaced from the headspace of a container being filled with a pure liquid chemical. A good example of this is if you are filling gasoline into your car when you go to a gas station. So air is being displaced from the headspace of your gas tank in the car when you are filling it with this chemical, which is liquid gasoline. So if we assume that the headspace air is saturated with the chemical's vapor, the volumetric rate at which the container is being filled provides a worst case vapor mass emission rate into the airspace outside the container. So let's assume that the volume of the container is V sub CONT in units of cubic meters. Let's assume that the volumetric filling rate, the rate at which you're filling the gas tank, is F in units of cubic meters per minute. C saturated is the saturated vapor concentration, and in units of milligrams per cubic meter. So the vapor mass emission rate in units of milligrams per minute is given by the product of the saturated concentration of the vapor times the volumetric filling rate of the liquid. And so if you see the saturated concentration, that has units of milligrams per cubic meter, and the volumetric filling rate has units of cubic meters per minute. And so the vapor mass emission rate has units of milligrams per minute. So this is the rate at which gasoline vapors are leaving, escaping the gas tank. And if you a modern gas filling at gas stations, you have a cap that captures the leaking around the opening into your gas tank. So you don't actually see this that much. But if that seal were not there, you would be exposed to the components of gasoline which are escaping at a particular rate, milligrams per minute, from the gas tank. Another important model that can be used to estimate airborne concentrations is something you might have learned in physical chemistry during your undergrad freshman chemistry class, and it is known as Henry's law. So let's consider a particular chemical in an aqueous solution. Let C sub A, air, denote the concentration of the same chemical A in air, again in units of moles per liter of air or milligrams per cubic meter of air. So in a closed system of air and water at equilibrium, the partitioning of the chemical A between air and water is given by this dimensionless Henry's law constant, denoted by the ratio of the concentration of the substance A in air and the concentration of the same substance A in the aqueous solution or in water. So basically what Henry's law is saying is that when you have, let's say, a substance such as benzene in water, then some of the benzene escapes from the water into the air above it. And there is an equilibrium set up between the benzene molecules in the air and the benzene molecules in the water. And that equilibrium concentration in air and liquid is denoted by this Henry's law constant. And the Henry's law constant is specific for a chemical A in water and air, and it depends on the temperature of the system. So how can we use this Henry's law? Let's look at this example. So let's assume that benzene is in a aqueous solution containing 10 milligrams of benzene per liter of water, and a tank containing 1 cubic meter or 264 gallons of the solution is in a closed room at 25 degrees Celsius, and the volume of the room is 100 cubic meters. So volume of the tank is 1 cubic meter. The volume of the room in which the tank is placed is 100 cubic meters. Let's also assume that the room has no airflow through it. So Q is 0 cubic meters of air per minute. We will assume that equilibrium has attained between benzene and water and benzene and air. And so now, what is the benzene concentration in air? And we are given the Henry's law constant for benzene in air and water as 0.22 at 25 degrees Celsius. So we start off by doing a mass balance for benzene and water. So the initial benzene mass in water is equal to the final benzene mass in water plus the final benzene mass in air. So as I said earlier, the benzene concentration in the liquid is 10 milligrams per liter of water. And we also know that the tank contains 1 cubic meter or 1,000 liters of water. And so therefore the initial benzene mass in the liquid is 10,000 milligrams. So 10 milligrams per liter times 1,000 liters. At equilibrium, the benzene mass in air and water must equal 10,000 milligrams. So the next equation shows how the benzene has now distributed between the air and water. So the concentration of benzene in air is denoted as C benzene times the 99 cubic meters that are air in the room, plus the C benzene in the aqueous solution times 1 cubic meter, which is the volume of water in that tank. And this must equal the 10,000 milligrams of benzene that you have in the water initially. We know the Henry's law constant for benzene in air and water, and that is 0.22. So the benzene, C benzene in air is equal to 0.22 times C benzene, the aqueous solution. And we can put this relationship in the equation above, and we can then solve for this mass balance equation for C benzene. So we have 0.22 times C benzene aqueous times 99 cubic meters plus C benzene aqueous times 1 cubic meter is equal to 10,000 milligrams. So when we solve for C benzene aqueous, that comes out to 439 milligrams per cubic meter. And then we can therefore calculate the C benzene in air, which is 0.22 times C benzene in the liquid. So that comes out to 96.6 milligrams per cubic meter. This represents a benzene concentration in air of 30 parts per million, which is 30 times the OSHA 8-hour time-weighted average permissible exposure limit and 300 times the NIOSH recommended exposure limit. So this clearly represents an unacceptable exposure scenario, and we were able to determine this by not making any measurements, but just considering what the scenario is, meaning we looked at the fact that it was just benzene in a liquid in a room with no airflow in it, and we were able to estimate what the benzene concentration in the air was.